Ladies and gentlemen, my name's Paul, and in this Games.com video, we have an exclusive interview with Nvidia. We're going to be discussing ray tracing, graphics technology, APIs, game engines, and a lot more besides. So I'd like to thank Nvidia along with Nuno for his time. There will be a follow-up to this interview at some point in the early part of next year. But enough of me blathering on, let's get on with the interview. Hi there, Nuno. Would it be possible for you to introduce yourself to the audience, please?
Of course. So my name is Nuno Subtil. I'm a Devtech Engineer at Nvidia. That's our cute name for developer technology, I guess. And so what we do is we help developers make their applications great. And in my case, I'm focused on the gaming market and more specifically on the Vulkan API and all things related to Vulkan. I've been also doing some work on ray tracing within Vulkan specifically, and in the past I've held other positions at NVIDIA as well, ranging from system software engineering, driver software essentially, as well as some more research-oriented positions around topics like DNA sequencing and other such things.
Wow, that's really cool.
Yeah, it's a great conversation starter for sure.
Yeah, you're not exactly limited in your field of expertise, at least.
Yeah, I would say my focus has been primarily graphics throughout my career. I just did a detour, so that's kind of what happened.
So now, obviously, the GeForce 20 cards are out. I guess what my first question would be is, what type of feedback are you receiving from developers regarding the changes in the architecture itself? Because obviously there's been so many different tweaks with the Turing architecture.
Right. So the feedback we're getting is positive, right? It's quite a good change for developers. Obviously, we've made a big bet on features. We've released ray tracing support and hardware with Turing, and that's kind of a really big deal. That's getting a lot of really positive feedback from developers. But of course, that's not the only thing that we did with the architecture. There's a number of under the hood improvements, just general performance improvements that are having a pretty good impact on many existing titles, as well as other graphics related features that we've built into Turing, which are getting really positive reception as well.
So when you were designing Turing itself, I guess this is more of a general question, but do you feel that you overall hit the design goals that you were aiming for?
I would say so. So that's kind of a tricky question to answer, since the design process isn't necessarily doesn't necessarily make that question easy to answer. Overall, we figure out early on which features we want to get into a given architecture, and what kind of performance we're targeting and how we're going to get there. And by and large, yes, I believe we've succeeded at that.
Can you actually explain what ray tracing is and why it's so important, especially for gamers?
Right. So ray tracing, and specifically real-time ray tracing, has been described as the holy grail of graphics for a really long time. And so we believe Turing finally makes that mainstream. And typically, real-time graphics so far has been based on rasterization, which is an algorithm where you have your data sets, your characters in your game, your scenery, etc., is built up of triangles in 3D space. And with rasterization, you just go through the triangles one at a time, you project them back onto the screen, and then you paint them essentially by computing each pixel's color, right? And so the fundamental problem with rasterization is great because it's very amenable to hardware implementations and very efficient in hardware. The fundamental drawback is simply that when you're drawing a single triangle, you don't have access to information on other triangles. You can only get access to whatever information you can attach as values to and attached to the vertices that get interpolated within the triangle, or indirectly through, say, texture lookups on something that you computed beforehand. One simple example being shadow maps, which give you sort of an approximate visibility function across the scene. but require you to process geometry twice, for instance. And so this limits what kind of interactions you can compute. You're essentially computing a function of the vertices and the data that's attached to the vertices, as opposed to a function of the scene around you for your lighting function, for instance. Now, with ray tracing, you do have the entire scene information available. So when you're computing your lighting model on any point, you can always evaluate the entire scene to compute your lighting model. So this means, for instance, shadows become naturally easy to do, where at a given point in 3D space, you can just sample the scene in the direction of a light. And if there's anything in that direction, you're occluded from direct illumination, right? That's a very simple example. More complicated examples would be computing accurate light transport information to determine indirect lighting across the scene, which is a huge component of lighting in general for realistic rendering. And so because you have the entire scene data available, you can naturally implement much more flexible algorithms, much more flexible lighting models that, as Jensen tends to say, it just works. It really just works, right? Well, another good example would be, say, reflections, where rasterization-based techniques seem to resort to using screen space data only, coupled with some lower res and lower sample frequency environment probes or something along those lines, where it's really tricky to get an accurate reflection even from a planar surface. You get all sorts of artifacts around the edges of the data that's available in screen space, and you have to blend that with environment map data and so on. You get sort of these strange artifacts sometimes that are really, really hard to blend these two functions together. Whereas with ray tracing, it's natural. You know what the incoming incident direction is, the normal, you just shoot a ray in the reflected direction and see what it hits, compute the shading at that location, and you incorporate that into the pixel color, and you're done. You get, perfect reflections that way.
So with ray tracing, Jensen points out, as you just said, that it just works. If you were to have a developer who is interested in incorporating ray tracing in one of their games, for example, let's say it's using Unreal Engine, how difficult is that to do?
So in general, we've made we went to great lengths to design APIs that are as easy to use as possible. And in fact, it's probably worth pointing out that our work on ray tracing APIs has started almost a decade ago, or even perhaps slightly over a decade ago, with the release of optics and the work that went into that. So we have significant experience on our side designing ray tracing APIs and shipping ray tracing APIs already. And so for a game engine, integrating ray tracing essentially means two things. You need to create what's known as an acceleration structure, which essentially is a different representation of your existing geometry. So take your existing geometry data, you feed it into this acceleration structure, and it's built in such a way as to be useful to accelerate ray tracing operations. This tends to be relatively easy since we can basically just reuse existing geometry buffers as is. There's typically no change required. We support pretty much all the formats and everything else that is common out there in engines today. So that's one part. And then the other part is just a kind of a transformation of your shader code to run as ray tracing shaders. In kind of a nutshell, that's all that's needed. And this, we've gone to great lengths to also make sure that this is as easy as possible. The shading language is obviously the same. Whatever shading language you're already using, we support it. And so it tends to be a natural fit to most engines. Of course, that depends heavily on the details, right?
So why has ray tracing been so difficult to achieve in real time?
That's a really good question. So ray tracing, I guess going back to rasterization, I mentioned it's very amenable to hardware implementations and very efficient hardware implementations at that. One of the key reasons is that the workload is fairly uniform with rasterization. So in other words, if you're computing color for pixels within a triangle, if you can kind of expect that neighboring pixels will execute in roughly the same time, for instance, and you can kind of use that to predict what the workload is going to be like across these work items that you're running on the GPU, and that makes it that gives a tremendous advantage when designing hardware, because you can leverage that to make the hardware extremely fast while keeping it relatively simple, at least conceptually. With ray tracing, that's not quite the case. So if you think of shooting rays into a scene, even rays that start out very close together can diverge completely during their path through the scene, and so it becomes very, very hard to exploit locality in terms of the workload and exploit this sort of uniformity, because it's essentially gone. So that's one big challenge that we've worked hard to overcome, is sort of the scheduling problem, where ray tracing is a very non-uniform workload, and we've spent many years working on this, and we've kind of achieved the solutions that seem to work well across a number of situations. The other part is obviously just the sheer calculations that are required to trace a ray through a scene, evaluate it against all of the scene primitives, all of the triangles in your scene, and return results as fast as possible. And so we've also invested a great deal of research and efforts into making sure that our culling algorithms are efficient and arriving at algorithms that can be implemented efficiently in hardware and so on. And finally, obviously, just besides culling, you also have to be very efficient at computing the actual intersection itself. And that was also an area where we've invested significant effort. So it's kind of a combination of these three factors coming together in the Turing architecture.
I've also heard some rumors, as well as the fact that you guys actually do with optics ray traced audio. So can the RT cores in theory actually run ray traced audio?
Absolutely. So ray tracing is not graphics specific, and this hardware was built to accelerate ray scene intersections. You can use that for many applications, including audio, visibility queries for AI. For instance, if you're trying to figure out whether an enemy can see a player, you can use ray tracing for that as well, and many other applications. It's not just graphics.
I think a lot of people get really hung up on that, and I've even had this conversation with a couple of people in real time, because people always associate of like RTX equals ray tracing. They kind of like skip over the rest of the stuff. But obviously, Turing is not just equals Pascal, but with ray tracing bolted on.
Right, and we're always very careful, even with optics, to position it correctly as a ray tracing SDK. It's not an image synthesis through ray tracing SDK. It's an SDK for casting rays through a data set, right? And you can always use that for many different applications, not just image synthesis.
What challenges do you believe are left with real-time ray tracing? Is it just simply optimizing the software and obviously improving the hardware? And how long do you think it's going to take before it becomes totally mainstream?
So we believe we're bringing it out to the mainstream with Turing. I think with graphics, historically, the experience has been that once a given piece of technology comes out, graphics developers immediately want more performance and more features and so on. And obviously with ray tracing, that's probably going to happen as well. But we believe we've reached a point where, and I think this is corroborated by the fact that titles are coming out with ray tracing features built in. We've reached a point where ray tracing is viable and is useful in a AAA game engine or in any real-time application for the most part. Obviously, hardware evolves, performance improves over time, and so on. And I think the amount of work you can do within the time span of a single frame within a game with ray tracing is obviously going to increase over time. But I do believe that we are at a point where ray tracing is already useful for common AAA games and any other engines that want to use it.
Because DICE and as well as Nvidia actually announced recently you've got an additional like 50% performance out of Battlefield 5 with ray tracing enabled as well. So I guess that's just kind of like one of those things where optimization is going to continue to evolve as developers get more used to actually enabling ray tracing in their engines as well, I'm assuming.
Exactly. I mean, it's both, it's a combination of improvements on our side, improvements on the application side. This is perfectly normal for any new piece of technology in the graphics world. Initial adoption tends to lead to more visibility into how we can improve the overall experience and how we can improve performance throughout the pipeline. And that's exactly what's happening. It's fairly par for the course, I would say, with any new piece of graphics technology, and certainly anything as complicated as ray tracing we will see these kind of leaps and bounds show up as developers and even ourselves get more acquainted with what actually the real world use cases for the technology, I should say.
Switching gears slightly to DLSS, I just wondered what steps roughly does a developer need to take to have their game run on DLSS? I understand that they need to submit it to Nvidia to run on your deep learning computers. So I just wondered like what the rough procedure would be for that.
Right. So I'll probably say that I'm not as involved with DLSS. I've done some work with DLSS before, but I am not as involved with that to say. There is some training involved, and there is. I think the process is variable enough that it really depends on the specifics of a given title. And I think that's probably about as much as I'm able to say right now. I can certainly put you in touch with people who can give you more detail if needed.
Yeah, that would be fantastic. I'll skip over the second DLSS question. I will actually ask it, but if you can't answer it, then I can always ask it to the next person. But obviously, we've seen deep learning and AI for imagery restoration from NVIDIA for some time now. For example, photos with missing parts of the image, or grainy photos, or colorization of photos. So was like the end goal of this technology that we've seen for photos, at least one of the goals, to be used in games all of the time in DLSS, or is it just kind of like a nice bonus?
I think I'm probably going to ask to skip. I would be able to give you an answer that may not be terribly useful, just in general, which is that we at NVIDIA, we see AI as a powerful force for change in the world in general, and improving many real world use cases of software in particular. And so there's not necessarily kind of this end goal of an end goal specifically. We just tend to do research on applications that we feel are useful and that we can productize.
How have prosumers, for example, once again, someone who perhaps does 3D Studio Max work, but also wants to play games, how have they responded to Turing, and what's the reception been with companies such as like Adobe and so on?
We've seen a very positive reaction from the professional visualization side of the market as well. Obviously, offline ray tracing has been in widespread use for offline rendering for the movie industry, for instance, and visual effects industry in general. And that's something that tends to get accelerated with GPUs whenever possible. And because of the way we've been exposing ray tracing to that market, Turing ends up being a plug and play upgrade, and you get an order of magnitude performance boost in many cases. And so obviously the reception has been incredibly good. Beyond just ray tracing, of course, we've always had extensive support for professional applications, 3D modeling, and so on. And Turing does deliver performance increases overall, which are always welcome in that market as well. Another interesting feature with Turing that helps with the kind of large data sets that tend to be common in professional visualization is what we're calling the mesh shaders.
I was just about to ask about those actually.
Right. Which really deliver or have the potential to deliver significant performance benefits when rendering large models and visualizing these really large data sets.
Yeah, because I had a friend actually, because I'm in the States right now, so most of my hardware's in the UK, including the RTX 2080 Ti. But I had
Right.
him run the Asteroids demo, which
Uh-huh.
had the Turing mesh shaders available, and obviously you can benchmark performance. And can you provide a little more insight into what Turing mesh shaders are and how they'll benefit games?
Right. Um, so mesh shaders are essentially uh, a way to condense most, if not all, of the pipeline for vertex processing into a single shader. So whereas you previously might have had, a vertex shader, hole in domain shaders, geometry shaders in the vertex pipeline, you can pretty much condense that into what looks a lot like a compute shader. So it's essentially running a compute shader to feed rasterization at a very high level. And what that enables you to do is do, for instance, a lot more efficient LOD calculations or level of detail calculations when rendering a mesh, such that, speaking of the asteroids demo or the asteroids scene, if an asteroid is really far away, you can easily pick a lower level of detail directly on the GPU without having to do separate passes to bucketize levels of detail per mesh or something like that. And you can also do do tessellation in line with vertex processing and so on, which essentially increases the scalability of the vertex pipe, right? And this is why it's useful for these really large data sets, because it becomes a lot easier, and the pipe becomes a lot more flexible to enable smarter culling algorithms and stuff like that. And so, typically when you're rendering a really large data set, a lot of the data is not actually going to be visible, and often there's some sort of acceleration structures or additional information you can feed into the process to enable efficient culling. And with mesh shaders, you can actually bring in this information and make use of it in line with vertex processing.
So I'm assuming developers, once they start to really incorporate this, we should actually see a larger performance bump still with Turing, especially in titles which really push a lot of geometry open world games where you've got large draw distances.
Yeah, that's agreed. Yes, that's that's our expectation as well. Again, this is new technology, and it sometimes takes a while for things to gain adoption. It's certainly we're certainly interested in seeing what developers will do with it.
Nvidia have said in the past that Turing is the greatest leap forward in graphics technology since the introduction of both CUDA and the unified GPU architecture. Would you say that this is still the case? I can certainly understand from the perspective of developers, it seems like they need to relearn so much stuff, much like when unified GPUs were becoming relevant. I believe it was the Tesla architecture back in the day, and even the GeForce 256, where we saw graphics architectures of the time move to shift triangle lighting from the CPU software side of things to the GPU.
Yeah, I mean, it's a little hard. It's easier to say in hindsight, obviously. When you're in the thick of it, it's hard to get that sort of perspective. Once the dust settles, it's a lot easier to understand that perspective. But yeah, it does seem like that's possible. I mean, Turing does have a lot of new features that are not just incremental improvements. They're, ray tracing is certainly a huge change, and it's a huge bet on our part. And so with mesh shaders, that's a similar situation. So yeah, it's entirely possible that we'll look back on Turing as kind of another big marker in GPU history.
Oh, speaking of shaders, or at least a variant of them, variable rate shaders slash content adaptive shaders. One of the last things I did while I was in the UK is mess around with Wolfenstein 2. And obviously that's just had an update using Vulkan to add in content adaptive shading. I believe that's like 10 to 20% performance boost is what we were roughly seeing at 4K, which is pretty darn impressive. We're also testing an RTX 2070, which kind of mirrored that. So can you provide some insight into exactly what variable rate shading does and how developers are going to be incorporating it in their titles?
So variable rate shading allows you to kind of change the sampling rate across the screen based on essentially whatever the game thinks is appropriate. Typically, this allows you to spend less cycles shading things that are not as visible. For instance, stuff that's in motion doesn't need as much detail as stuff that's static. That's one hypothetical heuristic you might be able to use, but in a nutshell, it's a more flexible way of controlling how much work is spent on different areas of your scene. And so we've developers have used that to really good effect in Wolfenstein 2. And I think we're going to see more and more titles adopt techniques like this to improve performance and kind of reach the performance levels required for 4K gaming.
Vulkan is really kind of coming into its own now. Obviously, id Software have really adopted it, but I was recently speaking to Neil Trevitt, and we were kind of comparing, almost, in kind of a joking way, like DirectX 12 titles and Vulkan titles, and it's really impressive, actually, how Vulkan is getting a great foothold in the market right now, particularly when you factor in that it's not just really good for, oh, I don't know, high-end desktops, it's great for laptops, it's great for cell phones, and so on.
Right. It does seem like there's been an uptick of interest in the Vulkan API in general. I think, at NVIDIA we support all APIs obviously, and we really don't pick sides. We support all APIs with the same level of dedication and quality. That said, of course, I did mention I am focused on Vulkan, so I am paying very, very close attention to the Vulkan API, and there's a lot of promise, and there's a lot of advantages to a cross-platform API, obviously. So if you're interested in supporting different platforms, DirectX isn't necessarily going to be enough, but you may be able to write your engine on top of Vulkan and write the code once and run it across many different platforms, whether it's Linux, whether it's mobile, or even older Windows platforms like Windows 7, where DirectX 12 is not supported. And so there is significant interest from that side. The Vulkan API, it's not fundamentally different from, say, the X12, but it does have differences that in some cases developers tend to say that it makes for a somewhat better API in some regards. But again, we don't really pick sides in APIs. We support them all, and we support developers with whatever API they choose.
What do you feel is the state of affairs when it comes to multiple graphics cards and systems? I mean, for example, Shadow of the Tomb Raider offers absolutely fantastic SLI scaling with DirectX 12, but other titles are more iffy at the moment. Like, what can you provide some reasons behind that and why SLI and multi-GPUs are, because AMD are obviously having similar issues, and what do you think it's going to start to become more prevalent?
So I think the main difference between DirectX 11 and the new breed of low-level APIs is that developers have more control over pretty much everything, and that includes what happens with multi-GPU. So with Vulkan, you're expected, as an app developer, you're expected to explicitly handle multi-GPU by making changes to your engine code to handle multiple devices rendering your scene. This gives you the visibility and the flexibility to control exactly what happens, and especially in terms of communication between the various GPUs that you're using, which is typically crucial to ensuring good performance across multiple devices. Now, obviously, with this control, there's a lot of potential to get really good scaling across multi-GPU systems. There's obviously some added work that the developer has to do in order to take advantage of this. With DirectX 11, there was a lot more that the driver would do. it was potentially less optimal in terms of the amount of data transferred across GPUs every frame and so on. So it would sometimes affect scaling somewhat, and we on our end we always try to minimize this sort of effect even on DirectX 11. But there's only so much we can do, and there's kind of some effort required as well on the application side to make things really smooth. But the potential for scaling was somewhat restricted in terms of the flexibility that we were able to expose to application developers through DirectX 11. Whereas with DirectX 12 and Vulkan, app developers have essentially full control, but they have to explicitly write code to make use of it. And so I think what we're seeing is for applications that add support for multi-GPU tend to scale pretty well on these new low-level APIs. And I think we just need to, it's just we need to encourage adoption of these APIs for multi-GPU support. And as that happens, I think we will see really good scaling across many titles.
So developers are interested. It's tricky to do, so they're still learning. Would you say that?
I wouldn't say it's tricky to do. I would say it requires a bit more explicit effort this time around, and that may not always be a top priority for developers.
Okay, that can make some sense. So one of the other questions regards open sourcing, because NVIDIA have recently released a lot of their software, GameWorks software, to open source. One of the big pieces of news over the last couple of days, of course, is physics. I believe it's 4.0 has become open source. Can you provide some insight into the reasoning behind this and how it's empowering developers?
I'm actually not deeply involved in these efforts, so I'd rather not speak about this topic specifically.
Okay, that's not a problem. What about, could you answer how you feel virtual reality is being adopted right now? Like, how do you feel? How does the general consensus of like VR in games, can you answer that type of question?
I could probably say that, obviously NVIDIA is committed to supporting VR or any other use cases involving our hardware. I don't actually have a lot of visibility into the VR side of things either. A lot of the features that we added for Turing are certainly very useful in the VR context. But again, unfortunately, I don't have enough visibility to give you a meaningful answer as to, adoption on the VR space and so on.
Speaking of which, there was also another major change with Turing as well, and that was GDDR6 memory. Would you say that that was a component that you were, I guess, waiting for release, and how instrumental has that increased bandwidth been for Turing?
I think in general, GPUs tend to always deal and be used in contexts that where memory bandwidth is crucial. Certainly in graphics, and memory bandwidth is a very crucial component of performance. And so when looking to improve performance for any new architecture, it's bandwidth is always a huge concern, and improving bandwidth while keeping within the cost envelope that we're trying to reach is always a crucial undertaking. I don't have any particular visibility into whether this was a strong concern for Turing, but obviously, bandwidth means performance improvements across the board typically when we're talking about GPUs. So it's certainly a big factor in doing our hardware design.
Earlier, you mentioned that the RT cores inside Turing can accelerate artificial intelligence, and of course, you've got the tensor cores in that as well. Do you believe that games are going to benefit in terms of their artificial intelligence from GPU acceleration, either with Turing or other such technologies?
So we certainly believe so. I should probably clarify my earlier statement about AI, which had to do more with classical AI algorithms that use path finding and require visibility queries being accelerated with ray tracing. But GPUs have been crucial in the current AI and deep learning boom, and we believe that's going to continue, and that's why we're investing so much effort and research into improving AI and deep learning performance on our GPUs, and certainly we expect that to be used for games. I you know, it's entirely up to what uses developers find for these algorithms. But we certainly expect this to be beneficial for gaming in perhaps short to medium term, I would say.
Okay, and what would you say is your? This is slightly slightly off topic, but what would you say is your favorite part of working at Nvidia?
I would say really the company culture is absolutely fantastic. There's a great deal of trust in each and every employee, and I think that goes a long way towards making people happy at NVIDIA. There's a great degree of freedom and independence, and in general, you know from the start that your manager trusts you, and as long as you do your best, that trust will continue. It's really a different culture from other places I've been in, and so I would say that that's the major factor in me and many other people being really happy at NVIDIA.
What would you say is your, aside from ray tracing, what what would you say is your favorite, or rather, what you feel is the biggest advance with Turing?
Well, in the shadow of ray tracing, it's kind of a tricky answer. I think meshlets, mesh shaders rather, would be probably the next on the list for me personally. I'm not sure if that matches what game developers will see, since that we haven't yet seen as significant uptake as with ray tracing, but that would be my best guess as to the next best feature.
I guess one of the last questions I'm going to ask is, when it comes to games developers and NVIDIA, how does the support network work with NVIDIA and games developers? Like, how do you guys work with developers to kind of implement the stuff? What type of help do they get? And with like driver issues and so on, like what kind of culture do you guys foster with developers?
So we try to be very honest and upfront, and we try to provide as much information and as much help as developers need or developers ask for. Obviously, that depends on specific developers, but in general, we just try to be as helpful as we can to make gaming on PC great, right? And it really, obviously, with any bugs that developers file, we try to be as responsive as we can and turn those around as quickly as we can. We try to provide information on performance and so on to developers so that they can decide how to improve their titles. I think it really depends on specific developers. Overall, we just try to be very honest, upfront, and helpful with all the developers that we engage with.
I can only speak from my personal experience here, but I have a lot of friends who don't know what the graphics settings do. Like, they barely know what resolution is. They know that, higher quality settings equal good, but they don't want to manually go in and configure stuff, and so typically they'll just leave the game settings pretty much by default. So has that been one of your goals recently with like GeForce Experience and the family of technology?
Well, that's actually really good to hear. We do believe that making PC gaming accessible is a big part of why the sort of boom or resurgence in PC gaming that you described may be happening. That's certainly something we put a lot of effort in, right? We try to bring out a product that is as polished overall as possible, and we consider the GPU as a package together with the software required to run it, and so we try to make that software as polished and as easy to use as possible. And certainly, that's why GeForce Experience exists, and there was a clear problem that gamers could use help with, and we've invested in a solution for that. I can say from experience that my gaming PC has GeForce Experience on it, and I don't need to worry about driver updates because it just handles it for me. My development PC doesn't because, well, I end up running random drivers all the time. So that's a different use case that isn't exactly covered by GeForce Experience, but that's perfectly fine, right? And then, as you said, PC builders that want to have control over their drivers may not want to use this feature of GeForce Experience, and that's perfectly fine. But we do believe that it solves a useful problem, and it makes gaming more accessible, and that's part of the reason why perhaps PC gaming is having a resurgence. My personal view, and this is just from personal observations, is that the esports scene has become a lot more popular, and that is primarily PC based for various reasons, and I believe that also has an effect in terms of the perception and popularity of the platform with gamers.
Okay, I think that just about wraps up the interview because I realise that you're pretty busy and it's coming up to Christmas period, so you've probably got about 20 deadlines that you need to finish off today alone.
Yeah, I mean that we yes, but that's not specific to Christmas. I think most days are like that, and I'm very happy to take the time. It's really a pleasure.
Thanks very much, Nuno, for your time. It's been an absolute pleasure, and hopefully we'll hear from you again soon. Is there any final words that you'd like to provide the audience?
Well, I think I would like to thank you and the audience for taking the time to listen, and I look forward to speaking again.
Okay, thanks very much. Take care of yourself. I'll see you soon. Bye.
Thank you. Bye.
Bye.